So we're going to talk about derivation of discrete Fourier transform from the complex form of Fourier series. So we have Fourier series f of t is equal to the summation k from negative infinity to infinity. The Fourier coefficient times e to the I k t, and the Fourier coefficient is equal to 1 over the period integral from negative t over 2 to t over 2 of the function e to the I k t. So here the function f of t is really given with a continuous time. Continuous. So that's why we use the integral to find the coefficient. But a lot of times in real life, or most of the times in real life, the function is not given to us. We have we can measure things. Say if we measure a chunk of signal, it looks like something like this. We don't have a f of t for this. It's just not given. But now how we're going to analyze it? We're going to have to use something else called a discrete Fourier transform. What discrete means is just you don't have time that's continuous. You take samples of the whole thing. If you take sample at discrete points, at some point in line in the time, because it's t1, t2, t3, t4, t5. Each time we have delta t, delta t, delta t in between. So t1 is equal to delta t, t2 is equal to 2 delta t, t3 is equal to 3 delta t, and so on. So that's these points right here, they all have a value that we measured. And these data are called discrete samples we collect from the function, the actual function. So we're going to need another way to analyze these discrete data other than Fourier series, because we don't have the continuous time function. So what happens if we change the time in here, to change to discrete time, Tn. So this becomes Tn. We have T1, T2, T3, T4, T5. We're gonna have something like this. F of Tn is equal to k equal to 0 to n minus 1